center picture was static mesh refinement of turbulence. The picture on your left-hand side is the Rayleigh-Taylor instability, which is one of the problems in the tutorial. So you can render some of the 3D data. Probably the tutorial doesn't have you run it at such high resolution, but nonetheless you should look sort of familiar if you've been doing the tutorial in 3D MHD. And then the images on the right are from a shock cloud calculation, which is also one of the tutorial problems. This is done in 3D with magnetic fields, and then it's being volume rendered. So again, if you have access to YT or Visit or any other 3D rendering program, and you take the 3D shock cloud data, you can begin to make kind of images like this. So by now, some of this is becoming familiar. So Monday morning, to remind you, was an introduction to the basic MHD integration algorithms in Athena, shared by many other Godunov schemes you're hearing about at this meeting. Yesterday, I talked about grids. I talked a little bit about Galilean invariance with grid codes, and I also talked about static mesh refinement and curvilinear grids as implemented in Athena. So today, I'm going to be focusing on extra physics. So a high-level overview of extra physics. Tomorrow, I'll talk about radiation hydro, and Friday will be applications. Again, interrupt me if you have any kind of a question. So a little more detail in today's lecture. I'm just going to sort of pick a few examples of extra physics and how it might be added into a scheme like Athena. So I'll start with something simple like cooling, and we'll talk about something a little more complicated like adding diffusion processes like viscosity, resistivity, and I'll talk about gravity, something that's important to add in many astrophysics problems. And then I'll talk about things that require very, very substantial changes, something like special relativity, and then adding dust particles. It seemed appropriate, since this is a meeting on star formation, to talk about dust particle gas dynamic interaction. So the bottom line is that the way that the physics is added depends very much on the mathematical nature of the terms that you're adding. And that should be no surprise. So there's basically sort of three kinds of changes. Simple changes, which require nothing more than adding a source term to the equations of motion, source terms which are completely local, don't involve any spatial operators. An example is optically thin cooling. It only depends on the local temperature and density, maybe the chemical species present, but it doesn't depend on gradients of things, and so it's a completely local term. More complicated changes are terms that require spatial operators like Laplacian, for example, so diffusion terms. So viscosity, resistivity, for example, and also adding more equations like self-gravity requires you to solve Poisson's equations plus add in extra terms to the equations. And then finally, some changes really cannot be listed as kind of just adding something to the code. It's really changing the code from first principles, starting again with something quite different. And I would say special relativity gets into that kind of. It's not quite such a substantial change, but it is a very, very big change compared to Newtonian. I think radiation hydrodynamics is the best example. It's really a complete rewrite of the algorithm to do radiation hydrodynamics. It's not sort of adding a radiation module, even though even I like to explain it that way. It's not really doing it that way. You really have to start from scratch. So let me give you some examples, starting with simple source terms. So the classic way, and this is where there's going to be a lot of overlap with what Paul already told you. This is where this is going to be good because I can just refer to his lectures and not have to give you all the same details all over again. But for adding simple source terms, it's generally done using operator splitting, a technique that he already explained. Basically, you just treat the terms in a sequential step. You do the flux divergence terms, calculating the fluxes as if there were no source terms, using the basic underlying algorithm, and then you update the source term using that partially updated quantities, and then you just cycle back and forth every time step, flux divergent source, flux divergent source. For Godunov methods, this kind of operator splitting formally makes the method only first order in time, so that's kind of a disadvantage. You're lowering the accuracy, formal accuracy of the scheme. And more importantly, again, as Paul discussed, this can lead to stability issues if the source terms are very stiff. If the source term is much bigger than the flux divergence term, then there should be a time step limit associated with that source term as well. And if you're not taking that into account, then that can cause you all kinds of stability problems. There's also even more subtle things, particularly difficult problem to solve, in fact one that you cannot use operator splitting for, is when the source term balances the flux divergence. So for example, if you have some steady flow where the flow of material is exactly balanced by some source term. So for example, maybe with chemistry, you have some flow of fresh material with some chemical reaction occurring at a rate which exactly changes the chemistry to give you a steady state profile in the Eulerian frame. That cannot be solved using operator splitting, because the flux divergence term will move the fluid without any chemistry. The source term will try to push it back to the way it was before. You iterate back and forth. It won't settle down to a steady state solution. So there are well-known examples where doing this kind of splitting doesn't work. And another good example is trying to hold hydrostatic atmospheres with Godunov schemes, where you have a pressure gradient determined by the flux divergence and a self-gravity term, or a gravity term set by an atmosphere. If you're going to try to have an absolutely quiet, stable atmosphere where there's no perturbations, then you cannot do operator splitting to add gravity to a Godunov scheme. You have to do it in a more complicated way. And there's a paper by Zingali, for example, which describes how you modify Godunov schemes to include self-gravity to have an absolutely quiescent hydrostatic atmosphere. If you want to do better than the simplest kind of operator splitting, and then again, as Paul has explained, I won't go into any more details, you can use multi-step methods, Runge-Kutta techniques, predictor corrector, so the Van Leer integrator in Athena or the CTU integrator in Theta can be modified to include the source steps directly in a multi-step way, and that'll increase the order of accuracy. If stability is the issue, then you usually have to go to implicit or semi-implicit methods. Either fully backward Euler differencing, or probably better would be something like Crank-Nicholson, which is a mixture of the advanced and the old times. So again, as he's explained, you have to go to implicit methods for very stiff source terms. So let me give you an example, optically thin cooling. So the term that you want to add to the energy equation, so here's our standard energy equation where Fe is the fluxes of total energy, which I haven't written out in detail, so Fe represents all of the contributions to the energy fluxes in the standard conservative form. But when we've added a term representing optically thin cooling and a term representing heating, so perhaps this is heating by starlight in the interstellar medium and cooling by radiative emission. Generally a two-body process, so there's a rho squared here. And then lambda is the per particle cooling rate, generally a function of temperature, but it could be a very nonlinear function of temperature depending on what cooling processes you include. So all the physics is kind of buried into this lambda, this cooling function, and there's many, many cooling functions available for different states of the interstellar medium in the literature. So again, as I say, depending on which function you're using, this cooling function could be very nonlinear and very, very stiff. And so if you use a forward Euler differencing, it can require a very, very, very small time step for stability. If you ignore the flux divergence terms, you basically have an ODE with a solution which is an exponential in time, and you're going to resolve that exponential, you have to have a very, very small time step. This time is smaller than the E-folding time. So better to use something like Crank-Nicholson, or maybe sometimes called a semi-implicit method, where you basically average the old and new times and then write the difference formula using the averages of that. And then because it's all local, no spatial gradients, then all you need to, every grid cell is decoupled from every other grid cell. You have to solve a nonlinear equation within each individual grid cell, but that's very, very straightforward using root finding methods. And so this is not difficult to add directly in an implicit or semi-implicit manner. Now if you want to do better than just simple operator splitting, you can add these source terms directly to the integrator itself. For example, when you calculate the left and right states in the reconstruction step of a Godunov scheme, you would include the cooling terms. You would modify the left and right states with the cooling term to give you better estimates of the left and right states. You then calculate fluxes from the Riemann solver, and then when you do the partial update, for example, in the Van Leer integrator to the half time step, you would include the cooling term for half a time step so that the partially updated value includes cooling, and then you would reconstruct the values and do the full time step by incorporating terms directly in the integrator. Then that gives you higher order accuracy and can lead to better stability properties. So the only warning I have, and again, climbing back on my soapbox, if you like, this morning on a different topic, it's easy to add such things, but you always have to remember that this is going to make the physics of the flow you're studying much more complicated. And so you have to be careful that not only you've added it realistically and accurately, but also that you're able to resolve or follow the physics of what you've actually added to the system. You've added a new length scale, a cooling length. You've added a new time scale, a cooling time. And you better make sure you resolve those length and time scales if you're going to have an accurate solution that's not dominated by truncation error. And so sometimes it could be a lot of work to figure out how the physics has changed and what the numerical requirements will be. They could be very different than what you had before. And so often you'll see in the literature, we studied this problem and we included cosmic rays, star formation feedback, radiative transfer, optically thin cooling, chemistry, self-gravity, relativistic effects. And you say, how did you do all that? That's amazing. Did you really go through all those terms and make sure? I mean, it's often easy to add lots and lots of physics, but be sure that it's all in there correctly and you understand what's going on is really very, very difficult. And so let me give you an example of this. A very, very simple example, the thermal instability in interstellar medium. So you just add this optically thin cooling and you're studying the states of the interstellar medium for the appropriate diffuse ISM cooling functions. As you probably know, there are the cooling function admits two stable states, a cold dense phase and a hot diffuse phase. And if you're in between those two phases, your cooling function will put you in an instability strip, and you'll either go to the cool dense phase or the other phase. So if you want to study this instability, well, in fact, there's linear dispersion relations for the growth rate of this instability versus wavelength calculated by Fields some time ago. So this is a classic Fields instability. So you know analytically what the growth rate should be as a function of wave number. So a very good test of your cooling function, your addition of cooling terms to the code, is to check that for a single mode perturbation, your code reproduces the linear growth rate of the cooling instability. Now the issue is that without thermal conduction, if you just add the cooling term with no thermal conduction, then the highest growth rate of the instability occurs at 0 wavelength. So the shortest modes possible grow the fastest. That's at the grid scale. So modes with wavelengths of delta x are going to grow the fastest. But those modes are unresolved on your mesh. They're completely dominated by truncation error. And so your physics is going to be dominated by modes growing at the grid scale. And that's not a good thing. So if you put in any kind of thermal conduction, again, this is known analytically, that cuts off the growth rate at small scales, because thermal conduction transports heat, it short circuits the thermal instability. The growth rate goes to 0 when you add in thermal conduction. So if you add thermal conduction and then do this test problem, the red crosses are the numerically measured growth rates for putting an exact eigenmode of the thermal instability of different wavelengths and then following its growth. And reassuringly, the code reproduces the growth rates very, very well, so you know you're on the right track. So this is checking the linear regime. What happens when you go to the nonlinear regime? Well, if you just do a thermal instability calculation with no thermal conduction and you run into the nonlinear stage, this is the picture you get. Everything fragments into this very diffuse or very dense phase, these tiny little cloudlets, very, very dense blobs. And that's what happens when you put in just a little bit of conduction, enough to be able to resolve the peak of the cooling function here. And you notice that these phases look very, very, very different. And this is all basically numerical grid noise. It's delta x noise, which has been amplified by the cooling instability at the shortest wavelengths and giving you little blobs that are no more than a few grid cells wide, whereas this is all resolved structure on the mesh. So it's very important, when you're doing this thermal instability, that it turns out you can't just add cooling by itself. You really need to put in thermal conduction as well if you're going to not have this grid noise being amplified. So that's an important issue. And so why is this happening as well? It's more than just the fact that thermal instability has this growth. There's another issue here, which is another unavoidable consequence of having a mesh to represent the fluid flow, and then adding source terms, which are very strong nonlinear functions of that mesh solution. And I'll call this overcooling in interfaces. It's a well-known problem. It's been around for 20 or 30 years, a well-known issue, which you have to have a special, have to be aware of and worry about in some circumstances. So what's the issue? I'll describe it through an example. So consider a problem which is the spherical D-type, dense type ionization front propagating in the interstellar medium. So you have a uniform medium, you set off a source of ionizing radiation at the center, it produces an ionization front which propagates away. Because it's a D front, there'll actually be a little shock front in front of the ionization front. There'll be a thin region of shocked gas and then the ionization front. And the equations you're solving here, a little more complicated than just cooling. There's also this ionization recombination occurring. So it's ionization recombination plus optically thin cooling in the equations of motion. So here's a calculation done with 3 different numerical resolutions at some time later on, so the ionization front is grown to some radius. And then shown above here, you probably can't read these scales very well, but plotted above are sort of a subsample of the grid points in the entire 3D volume to show you what the radial structure of this shell should look like, what this ionization front should look like. So here is the sound speed. This is the neutral density divided by the total density. So here it's completely neutral up to the ionization front, and then it's nearly completely ionized inside the bubble. And then the top is the temperature. So let's just focus on the temperature. Notice that the temperature, there are some grid cells which are in the intermediate regime between the cold dense phase and the hot ionized phase. So, and that's inevitable because the ionization front will never be less than 1 grid cell wide. It'll never be a true discontinuity. There'll always be at least 1 at best, but usually 2 or 3 grid cells that lie between the 2 states you're trying to resolve when you have a discontinuity on a finite mesh, especially in multi-dimensions. And so there's always going to be some cells here. And of course, you want to get as few as possible to make this as sharp as possible. And using higher order methods and good shock capturing techniques, get this as thin as possible. But you're never going to make it absolutely thin with no grid cells there. Okay, fine. So why is that a problem? Well, the cooling function is a very nonlinear function of temperature and density. In the hot, low density phase, the cooling rate's very small because the density is so low. So rho squared times lambda of T is very small because rho is so small. Very small cooling there. In the dense medium, well, the cooling rate there is very small because the cooling function itself is small. T is small, so lambda of T is small. Of course, rho squared is big, but it's multiplied by lambda of T, which is a small number. So the cooling rate in the undisturbed medium is small. But in between, it's the worst of both situations. Neither the density nor the temperature is small. The density is an intermediate value. Rho squared is going to be big. Lambda of T is an intermediate value. Lambda of T is going to be big. There's going to be a huge cooling rate right in the middle. And that can be a problem. If you go back to the thermal instability, at the edge of each of these grid cells, there can be an extremely large cooling rate for the 1 or 2 grid cells that are right in between the density of the hot and the cold phases. And you have a much too high, an unrealistically high, numerically incorrect cooling rate at those interfaces. And if you allow that to happen, it can sap a substantial fraction of the overall energy in the flow. You can lose 20–30% of the energy, thermal energy in the medium just from overcooling at these interfaces. So if you're not aware of that, you could be getting the incorrect solution. You have to do something special. This is the sort of thing that you have 2 solutions for. One is easy, a bit of a kludge but straightforward. You simply calculate the cooling function itself, cooling rate, I should say. You calculate the cooling rate, and if there's ever 1 grid cell where the cooling rate is, say, 10 times higher than any of its neighboring cells, you cut it off. You say, I don't believe that cell. That's 1 cell. I never believe anything that's only resolved by 1 cell. So instead, I'll replace this 1 cell with the cooling rate, which is the average of the neighboring cell, and that'll shut off all the unphysical cooling in these interfaces, and that works extremely well, it turns out. The other option is extremely complicated. Somehow you have to add in an interface tracking method and be able to distinguish between cells which are partially mixed, containing half hot fluid and half cold fluid, and calculate the cooling rate from the mixture of hot and cold fluids correctly. Question?
I don't understand how just averaging over, so if you have a really structured cooler in only 1 cell, how that works. Because you said that generally it's spread over 2 or 3 cells.
2 or 3 is, 1 is actually typical for a Godunov scheme. 1 cell is typically where the peak occurs. So you're right, it depends on your scheme. If you're using a diffusive Riemann solver like HLLE, it may spread interfaces over more than one cell, maybe 3 or 4 cells. Then you'd have to worry about that. And then perhaps only having one cell is not going to be good enough. But this is exactly the issue. You have to understand your numerical scheme and exactly how it's treating interfaces to figure out what's going to work here. If you just blindly add the cooling function in and run it without worrying about these sorts of issues, you can get yourself into trouble. So, you know, I'm not going to say there's one general solution. It really does depend on your scheme. In my experience, you're doing third order with a good Riemann solver, one cell is good enough. And that'll cut off the cooling function.
And also, in general, you know, it's nice when you have these nice spherical ionization fronts and stuff. But if you a real problem,
yes,
it's more complicated than that.
absolutely.
So,
But this is still a general point. And in more complicated geometry, along that interface, you're still going to have individual cells, no matter what its geometry. And so you always have to make sure that you are, you know, checking the cooling rate to make sure there's no unphysical cooling rates. I mean, think about what you want to do is monitor the cooling rate that you're actually adding to the equations of motion. And if there are features in the cooling rate which are unresolved, you don't want to allow those features to be included in the equations of motion. You need to cut them off some way, either by some limiting or a better algorithm prevents those features from growing. So a good diagnostic is just to take your solution, take the cooling rate that your code is using and just look at it, just visualize it. And if you see lots of regions of one grid cell or 2 grid cells where the cooling rate is order of magnitude larger than everywhere else, then you have to start getting worried about what's going on. Okay, so yeah, sorry.
It just seems a little strange that it's not you're not taking the limit of large temperatures or the limit of small densities or something in these cooling rate equations, and so that they break when you're reaching these middle density and temperature values. So at least for the numerical implementation, I mean, is that you never want to reach whatever these middle densities are that's in between the grids, in between the shock upstream and downstream gradients.
I mean, the cooling rate, the cooling function is well posed. It's correct over this range of temperatures. It's not like there's some unphysical region of temperature space where the cooling rate is wrong. This is the correct cooling rate to be applied over this range of temperature. And moreover, the density dependence of the cooling rate is correct. It's the right thing to do for this range of densities. You know, the problem is that the numerical solution at this interface is not correct, right? It's an approximation to what should be a discontinuity, but instead there's a cell that's in between. And that has an associated cooling rate. I mean, this is fine for the hydrodynamics. This intermediate cell does not change the structure or propagation of this interface in the Euler equations. But when you add in these source terms, they connect, you know, they sort of feed off the cell at the intermediate value and produce an unphysical solution that way. It's the interaction of the source term with the ideal hydro solver that's causing the problem. So that's why you have to worry about putting this fix in, I think. And you don't want to put a limit in because during the growth of the cooling instability, there were times when that intermediate density and temperature was real. It was a resolved feature as the temperature was changing, and you wanted to have cooling at that rate. That's what drove the cooling instability all the way to the nonlinear phase. And indeed, in fact, when you've added in thermal conduction, then there are regions here where the density and temperature is in that intermediate phase, but they're now resolved evaporation fronts. With thermal conduction, you now have a resolved front with a width equal to the conduction length, where there's cooling at these intermediate states balanced by the right rate of conduction and advection in the fluid dynamics. You know, that's why this works better, because now you've resolved all length and time scales. There are no unresolved interfaces. There is no limiting needed to the cooling when you've added conduction in properly, because now you have resolved structures. It's when you don't have any minimum wavelength to resolve on your mesh that you have to put in this kind of limiter. So you have a true discontinuity.
There's no way to check the width of that discontinuity that estimates some length scale for it.
Unless there's some microphysics that you can add to set a length scale, like thermal conduction. And that's fundamentally what thermal conduction is doing, is it's introducing a minimum length scale that you can then try to resolve. You could also add in viscosity. That would put in a minimum length scale to the front. But of course, generally you don't want to do that, because then the amount of viscosity you need is very large, much larger than what a real astrophysical plasma would have. So now you're studying a viscous fluid, not an inviscid flow. And so it's a trade-off between trying to, this kludge I'm mentioning of cutting off the cooling function allows you to have an inviscid flow, a very high Reynolds number flow, and still correct this cooling, incorrect cooling, still having an unresolved interface without having it affecting the source terms. Okay? Okay, so hopefully that was a useful example of where just adding the simplest terms possible can actually be a little more complicated than they first realize. So let's go on to adding more complicated source terms, viscosity and thermal conduction. I just already mentioned thermal conduction. So how do you add it? Well, now you're adding a Laplacian operator to the right-hand side of the equations. But notice that you can write it as a divergence of a quantity. When you're dealing with conservative numerical schemes, you always want to write everything as a divergence of something if possible, because you know you can preserve conservation laws when you write it as a divergence of a flux. So when you add viscosity, you want to calculate the viscous fluxes at cell faces, then take the divergence of it, and you'll be guaranteed to conserve total momentum. If you write this term out as just a source term, you may not guarantee that you're going to conserve total momentum that way. So always, in a conservative numerical scheme, try to write everything as a divergence if you can. So similarly, the cooling rate is the divergence of the heat fluxes, kappa grad T. Nu here is the coefficient of kinematic viscosity, kappa is the coefficient of conduction. So the momentum equations would be modified viscosity, the energy equation modified by thermal conduction and by a viscous transport term as well, again, which can be written as divergence. So you can use forward time centered space, FTCS, differencing. For this, I think Patrick Hennebel in his first couple of lectures was mentioning about simple differencing methods for hyperbolic and parabolic equations. So FTCS involves a center difference formula for these Laplacian operators and a forward time integration algorithm. Now for hyperbolic equations at first order, this is unstable. But for parabolic equations like diffusion equations, this is stable. So this is a perfectly valid, stable differencing scheme. But unfortunately, doing the kind of analysis that Patrick showed you, you can calculate the time step limit by doing a von Neumann stability analysis, a Fourier analysis of the difference equations. You'll find that it has this delta x squared dependence on resolution for the time step limit. So when you go to very high resolution and delta x gets small, this time step limit gets very, very, very small. It's got a different spatial dependence than the CFL condition and the fluid dynamics. So the diffusion term usually puts a much more restrictive time step limit than the fluid dynamics does. And so that can be a problem. You don't want to be limiting your integration step because of the source terms that you're adding. So the only ways around this are the following. You can use sub-time stepping. That is, you take a bunch of small time steps at the diffusion time step limit for every single MHD time step that you take. That works for a few sub-time steps. You don't want to take 1,000 sub-steps. That doesn't make any sense. But if you're only taking of order 10, that's a simple, straightforward way to go. You can use something called super time stepping, in which the size of the time step is increased according to a very specific functional form. And what's remarkable is you can prove that that will remain stable even though you can increase the time step for the diffusion step to be larger than the formal stability limit. If you follow a particular functional form for the way that you increase the time step over time, this will remain stable. So by using super time stepping, you can reduce the number of sub-time steps you need to take per MHD time step. So that's become a popular way to go. The only problem with it is that it requires some unknown coefficients, which you have to sort of calibrate from your calculation. You don't know a priori exactly what the right geometrical form of these time steps you have to take is. Finally, as Paul has mentioned, you can use implicit differencing. So you would write the right-hand side of the diffusion terms using the advanced time solution, q to n plus 1. Q would be E here, or velocity if it's viscosity in a momentum equation. Of course, the problem here is that these equations involve spatial differencing. So now you're coupling the unknowns not just at the grid cell J, but also J plus 1 and J minus 1 in one dimension. And in 2 dimensions, there would be equivalently k minus 1, k plus 1. And 3D, you'd have yet another term. You'd have a 3-point molecule in 2D, and a 3 in 1D, 5 in 2D, 7 in 3D. And so that leads to a large sparse-banded matrix that you have to solve. In 1D, it's just a tridiagonal matrix. The only non-zero elements are along the diagonal. Tri-di matrices you can solve by Gaussian elimination in order n steps. That's really easy. But in 2D, it's going to be tri-di plus a band on each side, which is offset by the number of grid points in the x direction. And so you need some kind of matrix inversion method to solve that equation. Multi-grid, for example, is useful. That gets us into linear algebra, and I'm not going to talk about numerical methods for linear algebra, but multi-grid, conjugate gradient are all popular ways of doing that. But the point here is that you're beginning to get complicated. Now you're going to have to add in a module for solving large matrices every time step to do the implicit differencing, but that may be the only way forward if you're going to do very, very, very stiff viscous flows. Yes?
Which you want for a lot of these real problems.
What about SMR and AMR?
Won't that also complicate the whole process because you have to couple the solution on subgrids?
So each grid would have an equation that looks like this. And I think this all carries through to the AMR case. If you're doing implicit differencing, you would have to use multi-grid and iterate the solutions on all levels at once to convergence. If you're doing FCTS, you don't have to do that. You can just add the viscous terms explicitly, but again on each level. But each level you can think of as integrating its own unigrid with the appropriate boundary conditions from the prolongation step. I don't think there's any conceptual difficulties in doing AMR or SMR with these kind of source terms. But of course, if you're doing implicit differencing and solving elliptic operators implicitly, then there's going to be an implementation issue of solving these matrices across the AMR hierarchy. It's essentially exactly the same problem as solving Poisson's equation, of course. This matrix you're having to invert looks just like Poisson's equation. So if you're already doing Poisson's equation in an AMR hierarchy, then this is the same thing done again. Okay, so that's basically the way you add these terms. I mean, I don't know much more to say without writing down difference equations, or I think it's maybe getting to much too complicated. So, but maybe I'll point out that in real astrophysical plasmas, life gets a little more complicated quickly. So it turns out that in a magnetized plasma, these microscopic diffusion coefficients can have interesting complications. In particular, if you're in a weakly collisional plasma, then of course you have ions and electrons, charged particles, which are tied to magnetic field lines. They're gyrating around the magnetic field lines. And if it's weakly collisional such that it undergoes many, many gyro orbits before you have a collision with another particle, then both the electrons and ions are tied. Each individual particle is tied to the magnetic field lines before it can be jumped to another magnetic field line by collision. So thermal conduction is caused by transport by electrons, but since electrons can only move along magnetic field lines, then the thermal conduction becomes anisotropic. Thermal conduction is primarily along the magnetic field line, and there's virtually no thermal conduction perpendicular to the magnetic field line in this regime of a weakly collisional plasma. And similarly, viscosity is carried by the ions because they have all the momentum in the fluid. And if the ions are gyrating many times before colliding, then viscous coefficients are different parallel compared to perpendicular field lines. And so you need to add in anisotropic heat flux. So a heat flux which depends only, which depends on the direction of the local magnetic field here. So the appropriate form of the heat flux is this vector q here, where b hat is the direction, and normal vector representing the magnetic field direction in the local, your local field direction. So only B dot grad T is non-zero. Only gradients along the magnetic field produce the heat flux. Gradients perpendicular to the magnetic field produce no heat flux because you can't have electrons moving perpendicular to the magnetic field. So in fact, what you want to add in are these anisotropic heat fluxes. In the case of viscosity, this kind of anisotropic viscous is called Braginskii viscosity. In fact, I should mention that this is actually an approximation to the kinetic plasma physics that's going on that works in some regimes but not in others, as I'll mention in a minute. So in fact, what you want to do for weakly collisional plasmas, so that includes things like hot gas in galaxy clusters, that's a very weakly collisional plasma. The diffuse phase of the ISM, weakly collisional. Accretion onto a low luminosity accretion onto compact objects. So for example, the accretion flow in the galactic center around Sag star, that's a very weakly collisional plasma, and these kind of effects are very important for modeling that plasma. So rather than having isotropic transport coefficients, you should be differencing them anisotropically. And the numerics gets a little bit more complicated. You need to have in some kind of monotonicity preserving algorithm such that when you represent these operators on a finite mesh, you make sure that your fluxes are only parallel to the magnetic field directions. And there's papers I list here which explain how to difference these operators in such a way. And I'm going to embed a little bit of physics in here perhaps, or a little bit of astrophysics here. Why should we care? It turns out that these anisotropic transport coefficients make huge differences to the dynamics of the plasma. There's this new dynamics in the so-called kinetic MHD regime, something called the magnetothermal instability. So you're used to the conditions for convection being dependent on the entropy gradient. You should have learned this from your stellar structure courses at least, that if you have a stratified fluid in a gravitational field, then the fluid will be unstable to convection, so vertical transport of heat, if the entropy is decreasing upwards. So if the entropy is high in the bottom and low in the top, this will be convectively unstable. If the entropy is constant or increasing upwards, then that's convectively stable. But it turns out that you add in anisotropic induction, and that's no longer true. The convective criteria in this regime depends entirely on the temperature gradient. It doesn't matter what the entropy gradient is. It only matters what the temperature gradient is as to whether or not this is convectively unstable. And it turns out if it's hot on the bottom and cold on the top, that's convectively unstable. Even if the entropy is decreasing upwards, if it's hot on the bottom and cold on the top, that'll be convectively unstable in this regime. So you add in a tiny amount of anisotropic thermal conduction, and you qualitatively change the physics from this regime where entropy gradients matter to the regime where temperature gradients matter. So does this mean that stellar structure is all wrong? Because gosh, in stars, they're certainly hot in the middle and cold on the top, and yet we build stellar models based on entropy gradients. And the answer is, of course, no, because they're not in this kinetic MHD regime. They're dense enough that the particles undergo many collisions per gyro orbit, and heat transport is not anisotropic in a stellar interior. In fact, it's mostly carried by photons. It's mostly radiative diffusion, which couldn't care less about the direction of the magnetic field. And so in stellar interiors, you do not have anisotropic conduction, so this doesn't play a role. But it does play a role in the hot X-ray emitting gas in clusters of galaxies. So the thermal structure of X-ray emitting halos in galaxy clusters is actually determined by this magnetothermal instability, and yet another one, heat flux buoyancy instability. This is something that's come along in the last 5 to 10 years, and we've realized that the thermal structure of these clusters of hot gas in clusters is in fact dependent on these microscopic physics. So that's why putting in these kind of physical effects is interesting. So here's a calculation of the nonlinear growth of this convective instability in an atmosphere hot on the bottom, cold on the top. On the bottom, including no anisotropic viscosity. On the top, the more self-consistent case that includes it. And then just sort of to getting really into the physics here a little bit, but it turns out this Braginskii viscosity, in fact, is not really a very good description of the microphysics in itself. It has this constant coefficient of viscosity. But that's not actually correct, because when you have motions parallel and perpendicular field lines which are decoupled, you can get an anisotropic distribution function for the particles. Pressures along the field lines can be different than pressures perpendicular to the field lines. That's in fact what the viscosity really is trying to represent, the anisotropic pressure. Pressure is a viscous flux, and so an anisotropic pressure in the medium turns out to excite these Microscopic instability is called fire hose and mirror modes, and the growth of these instabilities can affect the dynamics. And so there's a whole huge effort underway right now trying to understand the role of these instabilities on astrophysical plasma. So, this is very much a research topic. So the numerics quickly leads into all kinds of interesting physics going on. So I think I may be taking a bit too long on these detailed topics. So let me move on to more physics, more terms to add. Ohmic resistivity. Let's try thinking about adding another diffusive process to the induction equation now instead of the momentum energy equation. Let's add ohmic resistivity. So that's due to collisions of electrons with neutral particles, which produces diffusion, degrades how they can move, and so produces a resistive electric field which resists motion. And so mathematically it's just added as another curl term in the induction equation. And by writing it this way, you should immediately realize the appropriate way to add this term to constrained transport algorithms for keeping div b equals 0. You immediately see that eta j is just another electric field, similar to the V cross B EMF that we've already talked about. And so the way you add in resistivity to make sure div b equals 0 is you add in a resistive electric field, eta j, at each grid cell corner. Then you use the CT difference formulas we talked about on Monday, and you then difference the induction equation with this resistive terms. That way you're guaranteed to keep div b equals 0 when you're including the resistive terms. So an extra constraint you have to worry about when you're modifying the induction equation with extra terms. Once again, the time step constraint can be very restrictive. You can use sub-time stepping, super time stepping. With CT, trying to write down an implicit formula for resistivity is very complicated. It not only couples neighboring spatial grid points, it couples all the magnetic field components together too. X, Y, and Z are all coupled together. And so the matrix you get is enormous, and its sparsity pattern is more complicated. And so I'm not aware of anybody who's done implicit CT differencing. So far, everyone has relied on sub-stepping or super time stepping to include in resistive effects when you're using CT to update the MHD equations. Now, there's more to life than just ohmic resistivity in an astrophysical plasma. In fact, in a weakly ionized plasma that's appropriate for the dense phases of the ISM or in protoplanetary disks. In fact, general Ohm's law says there should be not just the induction term, which is the term we've been including for ideal MHD. There should, of course, be the ohmic term, which we've just added. But there should also be a Hall term, J cross B, due to drift of ions and electrons from the collisions with neutral particles. And there should be an ambipolar drift term due to the drift between ions and neutrals, again, due to the differential collision rates between them. And so not only do we want to add ohmic terms, we like to add Hall terms and ambipolar diffusion terms. Again, with CT, you define, for example, a Hall EMF, which is just J cross B at cell edges. You then use CT to update the Hall EMF term. You can also add an ambipolar diffusion term. However, these terms are getting more and more complicated, and because of the spatial staggered mesh, there can be a lot of averaging required to get J cross B at the cell edges. So you have to sort of work through the difference formulas to get the appropriate centering of J and B to get these at the edges. So it can be complicated, but the way you have to go is calculate both a Hall and ambipolar diffusion electric field at the cell edges. And then good tests of this are linear waves with, for example, resistive effects. So there's analytic solutions for the damping of alphane waves with ohmic dissipation, for alphane waves with ambipolar diffusion. So here are plots of the fast alphane and slow modes with the dashed lines representing the analytic decay rates and the numerical solutions plotted on top. There is slight ringing here because these calculations are not initialized with an exact eigenmode of these resistive modes. So there's this slight superposition of linear waves which produces oscillations. But the decay rates are consistent with the analytic solution. So again, this is a good way to test with the analytic solutions. OK, so I've got time still to move on to an entirely different topic, gravity. Again, something that seems straightforward, but actually has some subtle issues in it, some interesting subtle issues to adding gravity to Godnoff schemes. Most importantly, what you really want to do is add everything as a divergence of a flux. So to add gravity to a Godnoff scheme, what you would like to do is add in the gravitational forces as a divergence of a stress tensor G. And the appropriate form for G is given here. So you want to calculate a stress tensor G. Small g is the gravitational acceleration, grad phi minus grad phi. So if you have a gravitational potential phi, you compute the gravitational acceleration small g, you form a gravitational stress tensor capital G, and then you take its divergence to add in the source terms of the momentum equation. Why do you do that? Because that way you conserve total momentum exactly, which is important when you're adding in these gravitational source terms. In the energy equation, the appropriate energy term is rho v dot g. I'll get back. This is not written in conservative form. This is a source term. I'll get to that in just a second. So if you have just a fixed gravitational potential, linear momentum is not actually conserved, but total energy is. So you can just add in, since momentum is not conserved with a fixed potential, then you can just add in the source term. You can either write it as this divergence form, or you could add it in. You're not conserving total momentum anyways with a fixed gravitational potential. You can conserve energy exactly, however, with a fixed potential by using the mass fluxes rho v returned by the Riemann solver, dotting them on to the analytic form of the acceleration from the static potential, and you can show that that will conserve total energy in a static potential property. But for self-gravity, as I say, you want to add in this term using the stress tensor. Of course, on top of all of this, if you're doing self-gravity, you have to solve Poisson's equation to get the potential. And I'm not going to say anything about that. That's a step that I leave to the reader. So you have to have some algorithm for calculating the potential, either using FFTs or solving the difference equations directly using multigrid, as we discussed, to compute the potential. Once you know the potential, then you can calculate small g here and build the accelerations from it. So let me just emphasize the importance of doing gravity in the conservative form. If you don't add in this gravitational acceleration through this divergence of the stress tensor, there's a very nice test problem in the literature which points out what will happen. If you just take a self-gravitating sphere in hydrostatic equilibrium, it should just sit there and not do anything. And now you advect this sphere across the mesh. It should again just coast along, maintaining its structure without evolving. If you don't add in the source terms in this conservative fashion, there will be some small truncation error which results in a net force on the sphere. And the sphere will either come to a rest or it'll accelerate on the mesh. The total momentum is not conserved. If instead you difference the gravitational source terms according to this divergence of a stress tensor, it will conserve total momentum, and the sphere will just continue to advect at a constant velocity. So this can be a big, if you're doing gravitational fragmentation calculations and you've got little self-gravitating clumps, they're generally moving with respect to the mesh, getting their kinematics correct requires adopting this form. In fact, another great test problem for this is fragmentation of acoustic modes. So basically Jeans instability, linear Jeans instability. Set up a uniform medium with self-gravity, excite a sound wave in it. If the wavelength of the sound wave is longer than the Jeans length, the sound wave will grow in amplitude and fragment. It's just going to be gravitationally unstable. So here's a test problem run with Athena of a rapidly growing, unstable linear sound wave which fragments into a blob in multi-dimensions. And if you can just track the total momentum of this wave as a function of time, and it should be absolutely constant. If you do this by adding a source term, this blob will either be moving or it'll have some unphysical velocity produced by the net truncation error, the net acceleration associated with the truncation error of the difference formula. 10 minutes, okay. Now it turns out that conserving total energy with self-gravity is very challenging, and that's because self-gravity is a non-local process, and calculating the energy fluxes locally depends on knowing the solution everywhere, and is a very complicated issue. But recently, there been pointed out that there are forms for the energy flux with self-gravity that you can use to build a numerical scheme which will conserve total energy with self-gravity as well as total momentum. And so if I go back to my equations, you would replace this term here, this source term in the energy equation, with a divergence of Fg, a divergence of a flux, and the divergence of the flux, this is one form of the energy flux with self-gravity that will preserve energy exactly. Now, if you look at it, it's a little bit ugly. It involves the gradient of the time derivative of the gravitational potential as well as the time derivative of the potential. But in principle, when you solve Poisson's equation in a discrete fashion, you can calculate both phi and phi dot, and you can calculate this energy flux, and then you can add it directly as a divergence to the system. And it does make a difference. So again, if you're doing gravitational fragmentation and collapse, then the heating of the fluid is mostly coming from the gravitational potential. The collapse is releasing gravitational energy, so most of the internal energy being released in the flow is coming from the gravitational potential. And so adding this term in as a divergence of a flux to conserve total energy can make a difference. There's a very sensitive test problem. You can look at oscillations of a hydrostatic sphere with a adiabatic index just a little bit bigger than gamma 4/3. This is when this is right at the stability boundary for oscillations of a hydrostatic sphere for n equals 3 polytrope. If you set up small linear oscillations of this hydrostatic sphere and you don't conserve energy, after a couple of oscillations it simply blows up because you have an unphysical thermal energy in the flow and it destroys the structure of the sphere. Whereas if you conserve energy exactly, this sphere will just keep oscillating stably right at the stability boundary. So there are problems you can show to demonstrate the importance of conserving self-gravity. Let me just say a couple of words about special relativity. This is actually a change which is sort of intermediate between a moderate change and a very, very complicated one. Intermediate because the equations of motion in special relativity look exactly, their mathematical form is exactly the same as the conservation laws in Newtonian frames. The only difference is that the definitions of the conserved variables and their fluxes are different. So instead of having mass, momentum, and total energy, we have proper mass, we have for momentum, and so on to conserve. And similarly, their fluxes are more complicated. Most importantly, everything is coupled through this Lorentz factor gamma, which is a function of all three components of the velocity. So the transformation between rest mass and proper mass depends on the velocity. So there's a nonlinear coupling in the transformation equations between the conserved and the primitive variables in special relativity. So all quantities are coupled together non-linearly. So that's really the only major difference. The underlying integration algorithm remains exactly the same. You reconstruct the primitive variables, you use a Riemann solver to calculate fluxes, you update them in a conservative fashion using one of the integrators I discussed before, for example, the Van Leeuwen split integrator. All the changes is that going from the conserved to primitive variables in the reconstruction step is a lot more complicated. You have to do this nonlinear root finding. There's a technique that by Noble et al. That works extremely well. That's what we use in Athena to do that inversion. And then you have to change the Riemann solver to be a relativistic Riemann solver. But again, in the literature, there's many exact and approximate Riemann solvers for relativistic hydrodynamics and MHD. So you replace the Riemann solvers you're using for Newtonian flows with the appropriate Riemann solvers for relativistic flows. And then finally, you can use this Van Leeuwen split integrator without any characteristic tracing. And that's that carries over with almost no change at all. And so, in fact, in the way you write the code, it's very, very similar to the Newtonian code. So it doesn't require that much change. You just have to change the transformation between conserved to primitive and slot in a new Riemann solver. And then you have a special relativistic code. So not so bad after all. And I'll skip the test problems of relativistic flows. And I don't think I can do all of modeling this in 5 minutes. So maybe I should leave this for Friday, because this is more sort of physics of protoplanetary disks. So I think I'm going to just sort of end a little bit early here. Maybe I'll take the time to show a fun jet. Now, this is a movie now, so now we can sort of relax a little bit, eye candy now. So once you get the special relativistic code written, you get these transformations in and the Riemann solvers, you can do some interesting applications. An obvious one is propagation of jets, because this is interesting from trying to model AGN jets, the propagation and structure of jets in active galactic nuclei. So here's a calculation of a propagation of a relativistic magnetized jet in a uniform medium. So it's a beam of relativistic fluid with a toroidal magnetic field embedded in it, propagating through a uniform medium. You can see the jet beam in the center of the calculation here. You see the formation of what's called a cocoon at the tip of the jet, produced by hoop stresses in the magnetic field confining the plasma to the working surface here. And then you also see K instability and rolls as the plasma flows back into what's called the cocoon, very low density. And this is rendered using VISIT, a useful tool for doing 3D analysis that reads VTK files directly. So you can take the VTK files that Athena generates and read them directly to VISIT to make these kind of movies like this. So lots of applications you can do with the relativistic MHD version. And I'll leave the particle integration algorithms, I think, for Friday as more sort of an application side of things than a numerical analysis kind of thing. So I'll stop here.